Okay, so today we'll start with equilibrium and acids and bases, and this is a video series which will cover everything that you need to know in terms of the equilibrium and acids and bases. So we'll start with equilibrium. What is equilibrium? And this part one will be introduction to equilibrium. If we see a reaction, let's say A is it's decomposed into B and C, then after we observe it, then we will see that some of the microscopic properties will be constant. And what we say in that case is that we say that the system or the reaction reached the equilibrium. So when we are talking about constant, like macroscopic properties, I'm talking about properties like concentration. So we see that the concentration of each reactant or the products is constant. Even pH, or when we see that the temperature is not changing anymore, or when we see that the pressure and the volume are being constant. So those are some of those that are known as the microscopic properties. However, what happened is that at molecular level, so those are all like big things, okay? Microscopic properties. But at the molecular level, what do we see is a constant change, okay? So we see constant change. And this is because products are becoming reactant and reactants are becoming products. Okay, so this change when the products are becoming reactant and the reactant are becoming products appears when we reach the constant at the macroscopic properties. So when we reach the constant at microscopic properties, then we notice that at the molecular level or microscopic properties, we see a constant change every time products are becoming reactants and reactants are becoming products. And you probably have seen this even when we express something like A plus B, and then you see this double arrow here, C plus D. So what this means is that the equilibrium on the microscopic properties like concentration, pH, volume, temperature, pressure, and so on is reached. However, at the same rate that A and B are produced, at the same rate C and D are produced as well. So we have this double arrow that represent that at the same rate that we are going from A and B to C and D, we will have B, C and D going to A and B. So when we see it from the microscopic big picture appearance, we think that the reaction have stopped. However, when what is happening constantly is that reactants are becoming product and products are becoming reaction at the same rate, at the same speed per se, quote unquote. So when the microscopic or the microscopic characteristics are being constant or stop changing, then we say that the system has reached the equilibrium. So when macroscopic big picture properties, things like, as I said, concentration, pH, volume, pressure, temperature are constant, are not changing, we say, we agree that the system, chemical system, of course, has reached the equilibrium. This kind of equilibrium is known as the dynamic equilibrium, because actually what is happening, it is whatever is still, products are becoming reactant and the reactants are becoming products. Okay, and at that point, what do we have is that we still have reactants present and we still have products present, of course, products. But at this point, we still have reactants as present in our solutions or gases or whatever state of matter we have as present. The proper definition of this is that the equilibrium is reached when the rate of forward reaction is the same as the rate of reverse reaction. So let's say we have situation when nitrogen, nitrogen 3 oxide is decomposed into nitrogen dioxide and nitrogen oxide gas. Okay, so when we see this, this is actually a reaction that happens in both directions. So, as I said even before, we have two, when the equilibrium is reached, when those macroscopic properties are reached, macroscopic characteristics are met, then we see two reactions. We see one side that dinitrogen 3 oxide is decomposed into nitrogen dioxide, and on the same rate, and nitrogen monoxide, and on the same rate, the nitrogen dioxide and nitrogen monoxide are forming the dinitrogen 3 oxide. Okay, so we see constant macroscopic properties like pressure, temperature, volume, concentration, even moles, but at the microscopic level, at molecular level, we have both reactions happening at the same time, at the same rate. So at the same time, we will have dinitrogen 3 oxide, and we will have nitrogen dioxide and nitrogen monoxide. Okay, so at the molecular level, what we will see is a constant rate that is changing, constant change, rate of change from reactants to products, and products to reactant. So at the same rate that the decomposition of dinitrogen 3 oxide is happening, at the same rate the formation of dinitrogen 3 oxide is happening. Okay, so this is just the start or the introduction of the equilibrium. Okay. Okay, so this is known, as I said, as the dynamic equilibrium, because it appears that is reaching the equilibrium, there is nothing changing. However, at the molecular level, what we see a constant change. Now, the way that we measure this is we measure it through that is known as the equilibrium constant. Or Kc. This is a law which is known in other words as a law of mass action, and it is formulated by two Norwegian chemists, Goldberg and Wage. Okay, and in general, what we have is, if we have an equilibrium that is reached between A and B to produce C and D, and as you notice here in this general equation, A and B are part of the reactant, and capital C and capital D are part of the products, while the lowercase a, B, C, and D are the coefficient. The equilibrium constant can be written as Kc is equal to the concentration, whatever is the product over the reactant. So concentration of C to the power of C times concentration of D to the power of D over concentration of A to the power of A times concentration of B to the power of B. Under this expression, which is known as the equilibrium constant, what we have to keep in mind is that coefficients become exponents. As you see here, A, B, C, D, lower cases are becoming exponents, and solids and liquids are not considered. So if the state of matter is solid or liquid, they are not considered. So what do we take into the consideration here, or what do we assume, is that capital A, B, C, and D are all as a gas state of matter. Okay, we'll see some examples now on how to calculate the equilibrium constant when the concentration of each of them is given, and then we will move to further questions. Let's take a look to this first example here, and let's write the expression for the equilibrium constant. What we assume here is that the equilibrium is reached, and then the reaction is in that is known as the dynamic equilibrium, which means that the reactants are becoming products, and at the same rate the products are becoming reactive. So the equilibrium constant for this will be as a concentration of NO2 to the power of 2, since the coefficient here becomes an exponent. And then we will have the concentration of NO to the power of 2 times the concentration of oxygen to the power of 1, which is nothing. Okay. Let's take a look at another example. And when we have example 2, when we have, let's say, fluoric acid in aqueous solution is with water and liquid is diluted. So then what we have is you do remember what this is. If not, then we will review it in a bit. So now, as I said, the first the rule for the equilibrium constant is the coefficients become exponents, and it is product over reactant as the rate, and liquids and the solids are excluded, are ignored. So the coefficient, the constant equilibrium for this particular reaction, since it is it's balanced, since it is balanced, will be the concentration of hydronium to the power of 1 times the concentration of fluoride to the power of 1 over the concentration of fluoric acid. Okay, and those are the things that we have to keep into the consideration. So if it is liquid or solid, then that compound is ignored. Okay. So now let's suppose that we have a reaction. So this will be example 3. Now let's not just write the concentration, the equilibrium constant, but we even calculate it. So let's suppose that we have a reaction as nitrogen monoxide and oxygen are producing nitrogen dioxide gas. It's gas. Okay, and on this experiment, what do we have is that the concentration of nitrogen monoxide is 0.0542 molarity. The concentration of oxygen is 0.127 molarity, and the concentration of nitrogen dioxide is 15.5 molarity. Okay, now let's calculate the equilibrium constant. So first, let's write the expression for it, considering the reaction that we have here will be the concentration of nitrogen dioxide to the power of 2, because it's products and then coefficients become exponents, over nitrogen monoxide to the power of 2, concentration of it, and oxygen to the power of 1. So now let's take this information and plug it in. So 15.5 to the power of 2. I have that tendency to write it with brackets even here. And then we will have, I think, 0.0542 to the power of 2 times 0.127 molarity. And when we enter this in your calculator, what do you have? Is 6.44 times 10 to the power of 5. Notice something, that the equilibrium constant is a number without any units, because concentration, molarity, so molarity and molarity are cancelled out, and there is nothing that it is no units on it. Okay, let's see another example, and this will be, I think, example 4. Again, where we are calculating the when we are calculating the equilibrium constant. Okay, so carbon monoxide plus chlorine gas, or CO2. Okay, gas. So now what do we have at a given temperature? At a given temperature, let's say at 75 degrees Celsius, what do we have is the concentration of carbon monoxide is 1.2 times 10 to the power of negative 2 molarity. The concentration of chlorine is 0.054 molarity, and the concentration of COCl2 is 0.14 molarity. Now let's write the expression for this reaction. So equilibrium constant will be, first let's make sure that everything is balanced, and usually will be balanced, COCl2 to the power of 1 over CO to the power of 1 times concentration of Cl2 to the power of 1. So this will be 0.14 over 1.2 times 10 to the power of negative 2 times 0.054. Okay, enter it in your calculator, and you will find that the equilibrium constant is 1.30 times 10 to the power of 2 to the power of 3, sorry, if we consider the correct sigdics, which will be 2 or to the power of 3, just 3. Okay. Now let's take a look at another example when the equilibrium constant is given and we are looking for the with what we are doing now, we are looking for the concentration of one of the entities. So this will be example 5. And with this example, we'll finish this part, example 5. Okay, so what do we have is, so we have decomposition of phosphorus pentachloride to phosphorus 3-chloride and chlorine. So phosphorus pentachloride gas is decomposed into phosphorus 3-chloride and chlorine. And this is happening at a temperature, let's say, at 250 degrees Celsius. And then what do we have here? The equilibrium constant is 1.05, and the concentration of phosphorus 3-chloride is 0.463, while the concentration of the phosphorus pentachloride is 0.875, and we are looking for the concentration of chlorine gas. Okay, so based on this reaction, first we check if it is balanced or not. Usually it is given to be balanced. We will write the equilibrium constant as Kc will be the concentration of PCl3 to the power of 1 because the coefficient is 1, concentration of chlorine to the power of 1, and concentration of phosphorus pentachloride to the power of 1. And from here, we'll substitute what is given. So the concentration is given to be 1.05. And we know that the concentration of phosphorus 3-chloride is 0.463. We are looking for the concentration of chlorine over the concentration of phosphorus pentachloride is 0.875. From here, we find that the concentration of chlorine will be whatever is 1.05 times 0.875 divided by 0.463. So will be 1.98 molarity. Okay.